Visualizing events. In approaching a probability problem, it usually helps, especially at the beginning when you're learning, if you could visualize the event that you want to find a probability for. There are a few ways to do that. One of them is called the contingency tables. In contingency tables, you're going to put your events in either a column or a row, and then the number of ways that they are possible to happen. For example, suppose um, we are drawing a card from a deck of cards, and the characteristics or the variable that we are interested in is whether we draw an ace card or non-ace card or the color of the card, red and black. So this is a contingency table for that event. We have the color of the card on the rows, and we have whether we have picked an ace or not on the column. And then we fill it out with the possibilities of this outcome. For example, we have a total of 26 black cards and a total of 26 red cards, which is going to be added up to 52. We have, for the black cards, 24 of them are non-ace and 2 of them are ace card. Similarly, for red cards, we have 26 red cards, 24 of them are non-ace, 2 of them are ace cards. That would add up to a total of 4 ace card and 48 non-ace card, which still would add up to 52. So this would also add up to 52. So if you visualize your data, your event, it's going to be easier to find the probability. So for example, if I ask you, we draw a card from a deck of cards, what is the probability of getting an ace? So we say, okay, we have a total of 4 cards. Then the probability would be 4 divided by 52. Or if I ask you, let me erase these lines. Or if I ask you, we draw a card from a deck of cards, what is the probability that you get a red ace card? So we have a total of 2 red ace cards, so that the probability of drawing a ace red card would be 2 out of 52. Or for example, what is the probability of drawing a black non-ace card? A black non-ace card, we have 24 black non-ace cards, so that would be 24 divided by 52. The probability would be that. So it would help us to solve the problem. Another way that we can visualize an event is using a decision trees. So in a decision trees, we start and branch out from the possibilities for each variable. For example, the sample space has a total of 52 cards, right? And suppose we want to break this down into the color and then based on whether it's an ace or not. So here we're gonna, at this point here, at this node or point here, we start, and we're gonna branch on based on the color of the card. So branch based on the color. So we're gonna branch out based on the color. We're gonna have 2 branch for red and black. We have 26 black cards and 26 red cards. And then next we are gonna branch out based on at these 2 points, we're gonna branch out based on whether we have ace or not. So let's do it for, we can do it for black and for the red card. So we're gonna branch out based on this ace card and non-ace card. We have 2 black ace card. We have 24 black non-ace card. We have 2 black red ace card and 2 red non-ace card. So similarly here, we can actually use this visualization to help us solve a problem. For example, what is the probability of drawing a red ace card? A red ace card would be 2 out of 52. So the probability would be 2 out of 52. 52. Or what is the probability of drawing a non-ace red card? A non-ace red card would be 24. So the probability would be 24 divided by 52. So visualizing is going to again help us to solve the problem. Another way to visualize an event is using the Venn diagram that you are familiar with. So this is how a Venn diagram works. We draw the sample space, but this biggest square here, so that's going to be our sample space. And then inside it, we're going to plot the diagram of each event, such as black, ace, and red, by a circle that you see here. So we have for the black event that you see here, we have this circle. So we have 24 total black cards. Also, the possibility of outcome of ace, we have 4 ace. Also, this is red, right? We have 26 red cards. 24 of them are non-ace. 2 of them are ace. Also, for black cards, 26 black ace, 24 non-ace black card, and 2 ace black card. So you can see the commonality between these circles. So there is no, of course, there is no red and black card. So that's why these two circles for red and black, they don't intertwine. So the intersection between ace and red is an ace and red card. And also we can find the union of these two events. So an ace or red. Using this, for example, we can find the probability of drawing a card that is either that is ace or red. Ace or red. So this is ace or red. That's the union of these, the yellow circle and the red circle. The union of these two would be these two. So that would be 24 plus 2 plus 2. Right? 24 plus 2 plus 2, that's 28 divided by 52. That's about 54%. That would be the probability of drawing an ace or red card. We need to learn about how to find the probability of or and. What is the difference between or and? So for example, this is going to be an and is an intersect. And is an intersect. Or, on the other hand, or is a union, as you see here. So you need to remember this. Or is the union, or is the union, and is the intersect, the commonality between two sections. Previously, we learned about simple events and joint events. Now we want to learn about the probability, simple probability and joint probability. A simple probability is the probability of simple event. A simple event is an event that has only one characteristic on one variable. For example, we draw a card. What is the probability of drawing a ace card? So ace is the type of card. That's one characteristic. So that's a simple event. Or drawing an ace, a red card. Red card is a color of card. That's one characteristic. So the probability of that is going to be called a simple probability. On the other hand, when we are talking about a joint probability, we are talking about the probability of an event that has more than two characteristics, two or more than two characteristics, which is called a joint event. For example, we draw a card. What is the probability of drawing an ace card and a red card? That means a red ace card. So here we have two events. We have two characteristics. We have the color and we have the type. So that's a joint event. The probability of that is a joint probability. Mutually exclusive and collectively exhaustive events. Mutually exclusive events are those events that cannot happen jointly, meaning they cannot happen at the same time. So every two events that cannot happen at the same time are called mutually exclusive. Let's see an example. If we draw a card, it cannot be red and black at the same time. That's impossible to happen. The probability of event red and event black to happen at the same time is 0. So that's why we call red and black are two events that are impossible to happen jointly, and we call them mutually exclusive. If you notice, these two events, red and black, belong to the same characteristics, and that's color. So the outcome of the same characteristics or variable are events that cannot happen jointly, and they are mutually exclusive. The collectively exhaustive events are those events that we are sure at least one of them is going to happen. For example, when we draw a card, it has to be either black or red. We are sure that the probability of being red or black is 100%. It cannot be pink, it cannot be blue, it cannot be any other color. It has to be either red or black. So black or red, black and red here are two events that are collectively exhaustive. Let's see another example. When drawing a single card from a deck of cards, the three events red, black, and ace are collectively exhaustive but not mutually exclusive. How come? So we have three events, red, black, and ace. So these are three events. They are collectively exhaustive, meaning these three events, at least one of them is going to happen. And it's going to be sure to happen, right? When you draw a card, it's either going to be a black card or a red card. It could be a red ace card or a black ace card. It's going to be any of these three. These three events, on the other hand, are not mutually exclusive. Black and red, these two, yes, they are mutually exclusive. They cannot happen at the same time. However, the other two, for example, ace and black, they can happen at the same time. We can have a black ace card. So they are not mutually exclusive. Also, these two, ace and red, can happen at the same time. We can have a red ace card. So they are not mutually exclusive either, right? So that's why we say these three events are collectively exhaustive, but not mutually exclusive. On the other hand, we can have events that are both, that are mutually exclusive and collectively exhaustive. We call mese events. For example, red and black are two events that are mutually exclusive, as we learned here, they are mutually exclusive, but also collectively exhaustive. So they are both. So black and red are both. So that's why we call the black and red mese. They are mutually exclusive and collectively exhaustive. The law of total probability, or LTP. Consider two characteristics or two variables A and B from the same experiment. Suppose B1, B2, and Bk are all possible mutually exclusive and collectively exhaustive outcomes of the second variable. That, if you remember, what this means is the probability of any Bi and Bj is 0. That means that none of these B1, B2 to Bk, none of them together can happen at the same time. On the other hand, the probability of at least one of them happens is exactly 1. So the probability of B1 happening or B2 happening or Bk happening is 1. We are sure that at least one of these is going to happen. This is called MECE outcomes of the second variable, or the partitions of sample space based on the second variable. Then the probability of any simple event of the first variable, A, is calculated using this formula. The probability of A is equal to the probability of A and BI summing up on all the BIs, meaning it's the probability of A and B1 plus the probability of A and B2 plus the probability of so on and so forth up to the probability of A and BK. This is called the law of total probability. To explain this better, let's actually look at an example. So in drawing a card from a deck of cards, suppose A is the type of card, B is the color of the card. All the possible mutually exclusive and collectively exhaustive outcomes of the color variable are black and red, right? That's the only two colors that we have. The probability of cards being black and red is 0. We cannot have a card that is both black and red. It's 0. So they are mutually exclusive. Also, when we draw a card, it's either going to be black or red. So they are also collectively exhausted. This is 1. So they are collectively exhausted. So black and red are the all possible outcomes of the variable B, which is color. So now based on this, we can find the probability of any simple event of A, for example, the type being ace. We can find this probability using this formula, the law of total probability, to break it down on the outcomes of the color, the second variable. So as you see here, we have, this is the sample space here, and we have the sample space. We have the black sets here, we have the red cards here, we have the ace cards here, these three events. So we want to find the probability of getting an ace. We can use it, the formula that we had to find that. Probability of getting an ace is equal to the number of ace that we have divided by the total number of cards that we have, S, the total sample size, which is equal to 4 divided by 52, right? 4 divided by 52. So we can definitely use this formula to do that, but also using the law of total probability formula, we can break it down to the colors output to do that. So it would be the probability of having a black ace plus the probability of having an ace, a red ace. Probability of ace is equal to the probability of having a black ace plus the probability of having a red ace, which is 2 out of 52 plus 2 out of 52, which is 4 out of 52. We get the same number. You might be wondering, why should we do that? The first formula was simple enough. Well, this is a simple example, but the law of total probability, when you can break it down to the outcome of another variable, can become really handy in more complicated scenarios and problems that finding the direct probability is difficult for us. So that's how we use the law of total probability to make it easier to find the answer. The next rule is the general addition rule. This rule states that the probability of A or B, we have or here, is equal to the probability of A plus probability of B minus the joint probability of A and B happening together. So this is how we can find the probability of A or B. Let's see an example. Suppose we want to find the probability of getting an ace or a red card. So here we have the example of drawing a card from a deck of cards. We have two variables here. We have the color, which we can have black and red, and the type of card, which here we only have the ace. Okay, so let's find the probability of getting an ace card or a red card. So we can use the formula that we learned before for the probability of event A would be the number of A's happening divided by the total number of ways that the sample size can happen. So that would be the number of A's or red divided by the number of S. How we can find the number of A's or red? The number of A's would be 4. So this is 4. The number of red would be 24 plus 2. So that would be 26. But if you notice here, these two here, these two cards have been counted twice, both for ace and for red. So we're gonna actually count them off here. So that would be 2 here. So that would be 4 plus 26, 30 minus 2, 28. 28 divided by 52. So this is how we can actually find this probability using our traditional formula. But according to our new formula, the general additional rule, we can also find the probability. The probability of ace or red is equal to the probability of ace plus the probability of red minus the probability of ace and red. The probability of ace, what is the probability of ace? That's 4 out of 52. What is the probability of red? 26 out of 52. What is the probability of ace and red? So for ace and red, we have 2 out of 52. So that would be 2 out of 52. 2 out of 52. Which is going to be 28 out of 52. Interesting question. If you draw randomly a card from a deck of cards and you are hoping for an ace, and I take a look at your card and I tell you, okay, the card is actually red. How would that change the probability of your card being an ace? Try to think about this question. This is going to be relevant to our next topic, which is the conditional probability. When we are looking for a probability and we have a new information. The new information here is you know that your card is red and you want to see how would that change the probability of your drawing a ace card. So let's see what is conditional probability.